The binding energy of an ionic crystal depends on attractive interaction between ions of opposite charge, repulsive interaction between ions of equal charge, and van der Waals interaction or van der Waals forces. See, binding energy of an crystal mainly depends on ionic attractive interaction. Attractive interaction is dominant for binding energy. Then comes the repulsive interaction. So both attraction and repulsion, binding energy depends on both attraction and repulsion. It depends slightly on van der Waals forces. So the option is the binding energy of an ionic crystal depends mainly on 1. Yes, it depends on 1 and 2. 1 and 2 and marginally on 3. Marginally is nothing but very small or very slightly. So option A is correct. Consider the free electron model of a divalent solid having simple cubic lattice with a lattice constant A. Let M be the mass of the electron. Consider a free electron model of divalent solid. In a divalent solid having a simple cubic lattice, there are 2 electrons per unit cell. That exactly fills the first Brillouin zone, which means that the volume of the Fermi sphere equals to the volume of the first Brillouin zone. So the option C is correct actually. The volume of the Fermi sphere is equal to the volume of the first Brillouin zone. Actually, this question has a lot of derivation and conceptual background about Fermi spheres and Brillouin zone. But to save time, just for time being, remember this that the remember that in a divalent solid having a simple cube, the volume of the Fermi sphere is equal to volume of the first Brillouin zone. The contact between metal and semiconductor is, see, if this is a metal and this is a semiconductor, when the metal touches the semiconductor, the electrons can move between them. That means the electron can move from metal to semiconductor and semiconductor to metal. Whether this movement of the electrons happens very easily or if the movement gets blocked, this depends upon the work function. So the contact between the metal and the semiconductor depends on the relative work function of the metal and semiconductor. See, when the metal and semiconductor are in contact with each other, there are 2 types of contact. First is ohmic contact, another is Schottky contact. The current from the metal and the semiconductor flows very easily in both the direction, then ohmic contact is formed. When there is no energy barrier, and current can flow easily from metal to the semiconductor, that means it is called ohmic contact. When there is a large energy barrier and when the current flows only in one way, that is when the Schottky contact is formed. The contact between the metal and the semiconductor depends on the relative work function of the metal and the semiconductor. In a crystalline solid with n number of unit cells, the number of the allowed independent phonon modes of the branch is. Imagine a crystal with bunch of the atoms connected by a spring. See, these are atoms that are connected by a spring. When these atoms vibrate, these vibration behaves like a particle, which is called a phonon. Each unit cell has the atoms that can move in 3 directions. That is, they can move in x direction, y direction and z direction. If this atom can move in x, y and z direction. When this atom vibrates in the x direction, it creates one phonon. If it vibrates in y direction, it creates another phonon. If it vibrates in z direction, it also creates another phonon. So this gives rise to different phonons in the different branches. Now, if the crystal has n unit cells, each branch can vibrate in n independent ways. So in a crystal that has n number of unit cells, the number of allowed independent phonon modes of the branch is n. So think of a crystal as a guitar string. Each tiny segment can vibrate in different ways. More segments, more possible vibrations. So the number of independent vibrations per branch is just equal to the number of the unit cell. So if the solid has n number of unit cell, the number of allowed independent modes of the branch is also n. In a metal A and B, the electron densities are Na, N, and B respectively. Their respective Fermi wave vectors are KFA and KFB. Then KFA is equals to KFB. If to solve this, see what they have given. They have given electron densities for metal A and metal B. For metal A, the electron density is Na, and for metal B, the electron density is Nb. And what they have given, their respective Fermi wave vector. Fermi wave vector for A is KFA, and the Fermi wave vector for B is KFB. And they have given a condition, that is KFA is equals to 2KFB. Now we need to find the relationship between Na and Nb. So for a free electron gas, the relation is given by N is equals to Kf cube divided by 3 pi square, where N is the number of electron density, Kf is the Fermi wave vector. So for metal A, Na is equals to Kfa cube divided by 3 pi square, and for Nb, Kfb cube divided by 3 pi square. Now take the ratio Na by Nb, that is Kfa cube divided by 3 pi square into 3 pi square by Kfb. If we take the ratio of Na and Nb, this will get cancelled, then Na by Nb is equals to Kfa cube divided by Kfb cube. Now the condition is Kfa is equals to 2Kfb. Then Kfa is 2Kfb whole cube divided by Kfb cube. That is 2 cube is 8. Kfb cube divided by Kfb cube. That is nothing but A. So N8. Na by Nb is equals to 8, or Na is equals to 8 Nb. Na is equals to 8 Nb. So option D is correct. A metal wire of radius r and the electron density n is carrying a current I. Then the drift velocity Vd for the electrons in this wire is given by. So what they have given? They have given the radius. They have given radius r, then electron density n, carrying a current I. They have asked drift velocity. So they have asked drift velocity. The electric current through the wire can be written as I is equals to NEA into Vd, where N is the electron number density, E is the electronic charge, and A is the cross-sectional area of the time, and Vd is the drift velocity. For a wire of radius r, A is equals to pi r square. Then I is equals to Ne pi r square into Vd. Now we need drift velocity. Drift velocity Vd is equals to I divided by Ne into pi r square. I divided by pi r square into Ne. So option B is correct. Match the following: Van der Waals bonding, ionic bonding, covalent bonding, and hydrogen bonding. See, Van der Waals bonding is seen in argon. Argon is a noble gas. In solid form, its atoms are held together by weak Van der Waals forces or London dispersion forces. Ionic bonding is seen in potassium chloride. See, KCl consists of K plus and Cl minus ions held together by strong electrostatic bonds or ionic bonds. Covalent bonding is seen in carbon. In diamond or graphite, carbon atoms are bonded by strong covalent bonds. Hydrogen bonding is seen in water molecules. Water molecules exhibit hydrogen bonding between H and O of the adjacent molecules. So 1 is 1. Ionic bonding potassium chloride, that is 3. Covalent bonding is seen in carbon, and hydrogen bonding is seen in water molecules. So option A is correct. In semiconductor strain gauges, when a tensile strain is applied. See, let us go with the basics. The resistance of any conductor or semiconductor is given by R is equals to rho L by A, where rho is the resistivity of the material, L is the length, and A is the cross-sectional area. Now in semiconductors, the resistivity rho is given by 1 divided by Qn into nu, where Q is the charge, N is the carrier concentration, and nu is the mobility. That means the resistance becomes R is equals to L by A into 1 divided by Qn into nu. That means here we can see that as mobility increases, resistance decreases. Here we can see that the resistance is inversely proportional to mobility. That means as mobility increases, resistance decreases. As mobility decreases, the resistance increases. Now when you stretch a semiconductor, two things happen simultaneously. See, when a tensile strain is applied to semiconductor, two things happen simultaneously. First one is geometric changes. And second one is band structure changes. In geometric changes, what happens is length increases and area decreases. See here, when the length increases and area decreases, that means resistance increases. In geometric changes. In band structure changes, what happens is mobility changes here. When the band structure changes, the mobility changes. For n-type semiconductors, mobility increases. When mobility increases, here we can see that the resistivity decreases. And for p-type semiconductors, the mobility decreases. When the mobility decreases, that means resistivity increases. Now if we summarize this whole thing, when you apply a tensile strain to the semiconductor, two things happen. Geometric changes and band structure changes. They happen simultaneously. Now in the what happens in the geometric changes is length increases and area decreases. Here from the relation we can see that when length increases and area decreases, resistance increases slightly. In the band structure changes, mobility changes here. Here length and area changes, here the mobility changes. For n-type semiconductor, mobility increases, that means resistance decreases. For p-type semiconductor, mobility decreases and resistance increases. In semiconductor strain gauges, when a tensile strain is applied. So when you apply a tensile strain to the semiconductor, resistance increases in n-type material. When a tensile strain is applied, mobility increases for n-type semiconductors and resistance decreases for n-type semiconductors. This option is not correct. Resistance increases for p-type material. Yes, resistance increases for p-type material because the mobility decreases for p-type material when you apply a strain, and resistance increases. Resistance increases in both p and n-type material. No. Resistance decreases. No. So option B is correct. This is the question for assertion and reason. In a pure semiconductor, the temperature dependence of the resistivity rho is given by ln rho is directly proportional to 1 by T. Let us check if this is correct or no. In a pure semiconductor, pure semiconductor is intrinsic semiconductor. So we know that in intrinsic semiconductor, the carrier concentration of the electrons is equal to the carrier concentration of the holes. Together we can say that Ni is the carrier concentration of the intrinsic semiconductors. This carrier concentration, the carrier concentration of the intrinsic semiconductor is given by A into T to the power of 3 by 2 e to the power of minus Eg by 2 kT, where K is the Boltzmann constant, Eg is the energy band gap. This is the carrier concentration of the intrinsic semiconductor. Now the conductivity sigma is given by E into Ni into mobility of holes, mobility of electrons plus mobility of holes. This is the conductivity. Now we know that resistivity is nothing but the inverse of conductivity. So resistivity is nothing but the inverse of conductivity, that is given by 1 divided by E into Ni into mobility of electrons plus mobility of holes. So we can say that rho or resistivity is inversely proportional to the intrinsic carrier concentration. So we can write resistivity as is inversely proportional to, see, intrinsic carrier concentration is this one. So in rho is inversely proportional to this carrier concentration. This term A is the constant, so we can leave that. T to the power of 3 by 2 e to the power of minus Eg by 2 kT, which is nothing but is directly proportional to e to the power of Eg by 2 kT. This term comes in the numerator, divided by T to the power of 3 by 2. Now if we remove the proportionality constant, resistivity is equals to C divided by T to the power of 3 by 2 into e to the power of Eg by 2 kT. C is the proportionality constant. Now apply ln on both the side. Ln rho is equals to ln of C minus ln of minus 3 by 2, which is nothing but 3 by 2 ln T plus exponential and ln gets cancelled, that is Eg by 2 kT. So here we can see that as temperature increases, this is constant, so we don't consider this term in the temperature. As temperature increases, since it is logarithmic of the temperature, this slightly decreases. As temperature increases, that means this whole term slightly decreases. Here the temperature is in the denominator, that means as temperature increases, this term also decreases rapidly, causing the whole resistivity to decrease. See again, as temperature increases, this term Eg by 2 kT, as temperature increases, here if this increases, because T is in the denominator, this whole term decreases. This term is the dominant term in the resistivity. This, since it is logarithmic, this we don't consider much, but this term, it is the dominant term in the ln rho. That means if this term decreases, if this whole term decreases, this resistivity, ln of resistivity also decreases. Thus we can say that ln of resistivity is inversely proportional to temperature, because as temperature increases, resistivity decreases. As temperature decreases, resistivity increases. So the first assertion which they have given, in pure semiconductors, the temperature dependence of the resistivity rho is given by ln rho inversely proportional to 1 by T. It is correct. That means A is correct. Now let's look at the reason. The intrinsic carrier concentration increases exponentially with the increasing temperature. See, the intrinsic carrier concentration. So the intrinsic carrier concentration, we know that Ni is equals to A T to the power of 3 by 2 e to the power of minus Eg by 2 kT. The intrinsic carrier concentration increases exponentially. Yes, here in this we can see that this intrinsic carrier concentration depends on the temperature from two sides, in the exponential term and also here in the 3 by 2 term. So the intrinsic carrier concentration increases exponentially with the increasing T. As T increases here, since it is exponential, this whole term increases, causing the carrier concentration to increase. So the intrinsic carrier concentration increases exponentially with the increasing temperature. Now in the options they have given A is correct and B, R is wrong. No, R is also correct, A is also correct. A and R both are correct, but R is not the correct explanation of A. Actually, see, in pure semiconductors, the temperature dependence on the resistivity is given by ln rho by 1 by T. This ln rho by 1 by T comes from the intrinsic carrier concentration. We derived this whole thing from the intrinsic carrier concentration. This relation is dependent on the carrier concentration. As the intrinsic carrier concentration increases exponentially with the temperature, this relation is true. As the carrier concentration increases with the temperature, this relation is true because we derived this thing from the carrier concentration. Okay, in a pure semiconductor, the dependence on the resistivity is given by this because the intrinsic carrier concentration increases exponentially with the temperature T. So assertion and reason both are correct, and reason is the correct explanation for A. So option D is correct. The relaxation time in second of the conduction electron is, the formula to calculate relaxation time is tau is equals to m divided by Ne square into rho, where m is the mass of the electron, n is the conduction density, E is the charge of the electron, and rho is the resistivity. These are all standard values for the conduction electrons. We know that the mass of the electron is 9.1 into 10 power minus 31, and the conduction electron density is given by 2.53 into 10 power 28. E is charge of electron 1.6 into 10 power minus 19 coulomb, and the resistivity is given by 4.7 into 10 power minus 8. These are all standard values. We have to remember these values. So if we substitute here, we'll get 9.1 into 10 power minus 31 divided by n is 2.53 into 10 power 28 into E square 1.6 into 10 power minus 19 square into 4.7 into 10 power minus 8. Then tau is equals to 9.1 into 10 power minus 31 divided by square of 1.6 is 2.56. So 2.56 into 2.53 into 2.53 into 4.7. It is 30.440 into 10 power 28. 19 into 2 is minus 38 and minus 8. Then tau is equals to 9.1 divided by 30 into 400. It is 0.29 into 10 power minus 31. 28 minus 38 minus 8. 28 minus 38 minus 8 is minus 18. If it is in the numerator, it becomes plus 18. And tau is equals to 30 minus 31 plus 18 is minus 13. So 0.29 into 10 power minus 13, or 2.9 into 10 power minus 14, which can be rounded up to 3 into 10 power minus 14 seconds. See, the closest option is 3.79 into 10 power minus 14. C. This formula is known as Drude's formula. Drude formula. For Drude formula, for metals or conduction electrons, this relaxation time comes up to be always 10 power minus 14 second in the magnitude of 10 power minus 14 second. I calculated here, but if they ask relaxation time for conduction electron or the relaxation time for metals, always look for the option that has 10 power minus 14. You don't need to calculate it. If we see the option 10 power minus 14, that is the correct answer. For metals, only for metals. For semiconductors, this comes up to be around, the relaxation time is in between 10 power minus 12 to 10 power minus 9. This also depends upon doping and temperature. So whenever they ask the question about relaxation time for metals or for the conduction electrons, look for the option that has 10 power minus 14. If it has 10 power minus 14, that is the correct answer. This is only for metals and conduction electrons. Since they have asked here for conduction electrons, so 10 power minus 14 is correct. The spacing between dislocation in the tilt boundary in FCC copper crystal when the angle of tilt is 10 degree. So the spacing between the dislocation is given by D is equals to B divided by 2 sine theta by 2. D is the Berger angle. And they have given Berger angle for FCC. They have given Berger vector. They have given Berger vector for FCC, that is 2.6 angstrom, and they have given angle of tilt theta. Theta is nothing but 10 degree. We have theta by 2. Theta by 2 is 10 by 2. That is nothing but 5 degree. So the spacing between the dislocation is given by D is equals to D is 2.6 divided by 2 into sine 5 degree. So sine 5 is 0.08 into 2. 2.6 divided by 0.17. So 2.6 divided by, answer is 2.6 divided by 0.17 is 14.91. So D is approximately equals to 14 point, if we look at the options, 75 angstrom. So option C is correct. In a n-type semiconductor, the Fermi level lies 0.4 electron volt below the conduction band. If the concentration of the donor atom is doubled, the new position of the Fermi level is at. So, in a n-type semiconductor, for n-type semiconductor, the carrier concentration is given by N is equals to Nc exponential of minus EC minus EF divided by KBT. This is the formula for carrier concentration for the n-type semiconductors. Now what they have given? They have given is the Fermi level lies 0.4 electron volt below the conduction band. That means they have given the value for EC minus EF. EC minus EF they have given 0.4 electron volt, and the condition is if the concentration of the donor atom is doubled, that means N is equals to N dash is the new Fermi position, the donor concentration is doubled, that means into 2N. So N dash, the formula N dash is the donor concentration. If it is doubled, it becomes 2N. So N dash is the new concentration, that is Nc exponential of minus EC minus EF dash divided by KBT, which is equals to 2 into N is Nc exponential of minus EC minus EF divided by KBT. Nc and Nc gets cancelled. Exponential of minus EC minus EF dash divided by KBT is equals to 2 exponential of minus EC minus EF divided by KBT. Now taking ln on both the side, this becomes exponential and ln term gets cancelled, that is EC minus EF dash divided by KBT is equals to ln 2 minus EC minus EF divided by KBT. Ln 2, sorry. Okay, now rearranging the terms, we get minus EC minus EF dash, sorry, EC minus EF dash. This is the new position of the Fermi level. They have asked the new position of the Fermi level. This is EC minus EF dash is the new position of the Fermi level after doubling the carrier concentration. EC minus EF dash is equals to EC minus EF minus KBT ln 2. They have given the value for KBT. KBT is 0.03 electron volt. So KBT is 0.03 electron volt, and we know the value for ln 2. Ln 2 is 0.693. EC minus EF value they have given 0.4. Then 0.39 in 0.03 into 0.693 is 0.02. 0.4 minus 0.02, 0.4 minus 0.02 is 0.371 electron volt. EC minus EF dash. This is the new position of the Fermi level. 0.0379 electron volt. So option A is correct. A free electron is placed in the magnetic field of strength 1 Tesla. The resonance frequency is, the electron spin resonance, that is ESR, is given by F is equals to G nu B by H. They have given the value for G nu B. B they have given 1 Tesla. H is Planck's constant. So G they have given 2.0023 into nu B is 9.27 into 10 power minus 24. B they have given 1 Tesla. 1 divided by Planck's constant is 6.6 into 10 power minus 34. So 2.0023 into 9.27 is 18.56 divided by 6.6 into 10 power minus 24 plus 34. It is nothing but 18.56 divided by 6.6 is 2.8 into 10 power minus 34 plus 34 is 10 power 10 hertz, or in the option they have given gigahertz. So 28 into 10 power 9 hertz. 10 power 9 hertz is nothing but gigahertz. So the answer is 28 gigahertz. 28.02 gigahertz. Okay. For a copper metal, the conduction electron density is this much. The Fermi wave vector. We solved this question earlier about Fermi wave vector. So we know the Fermi wave vector formula is Kf is equals to 3 pi square n to the power 1 by 3. They have given the value for n. Kf is equals to 3 into pi square is 9.86 into n value 8.45 into 10 power 28 to the power 1 by 3. Into 9.86 into 8.45. Kf is equals to 249.9 into 95 into 10 power 28 to the power 1 by 3. This Kf is equals to 2.49 into 10 power 30 to the power 1 by 3. 30 by 3 is 10. Kf is equals to 2.49 into 10 power 10 options are in the order of 10 power 10. Also we need to find the value of cube root of 2.49. Cube root of 2.49 is 1.35. 1.35 into 10 power 10 per meter. 1.36 into 10 power 10 per meter. I don't know how they expect us to calculate these type of problems without calculator. Okay, the next question. The electrical resistivity of the metal at 300 Kelvin is this much. The Lorentz number is this much. The thermal conductivity. Okay, we know the formula for Weismann-Frank's law. Weismann-Frank's law. Thermal conductivity K is equals to L into T into sigma. What they have given? They have given electrical resistivity. So we know that sigma is equals to 1 by rho, inverse of resistivity. So thermal conductivity is 1 LT divided by rho. So K is equals to Lorentz number. They have given 2.45 into 10 power minus 8 into temperature 300 Kelvin divided by resistivity is 4.9 into 10 power minus 8. So the options are very far away, so we can do approximation. Take this as 2.5 into 10 power minus 8 into 300 and take this value as 5 into 10 power minus 8. 10 power minus 8 get cancelled. If we remove the point here, we'll get 10. 5 5s are 25. 0 and 0 get cancelled. Then K is equals to 5 3s are 15. 150 Weber per meter per Kelvin. So option is 150. If they give this type of questions, we can calculate easily. Okay, next questions I will solve in the next video. Thank you.